Okay, well, I'm Susan O'Neill, and I'm here. With Forest Service Research, and so I'm going to be talking about air quality and visual range, and I'm going to be kind of giving a story about it. So we just heard about what specifically is being done in New Mexico with the 531, and so this is sort of like a little bit of a bigger perspective and kind of where this whole linkage of visual range to air quality started, and it also gets into some of the uncertainties with it, which Ken, you touched on already with, just a human sighting of visual range, and trying to decide whether it's 1 mile or 1.25 miles. There's a huge uncertainty there. So, okay, go ahead. So this all started with, what do you do? Like you said, what do you do when an atmosphere is smoky? There's some smoke concentrations, but you don't have a monitor, and so you don't have a PM 2.5 measurement. But you have games you want to schedule, high school football games or baseball games. You have different activities going on outdoors, and you don't know what level, what you should be telling the public. But you just know you look outside and you know that things are smoky. So how can you use that information? And so, when you have a monitor that does a 24-hour measurement, then you can compare that to the National Ambient Air Quality Standards. But we know in a wildfire, smoky situation that typically a lot of times the smoke is there and gone. Things can be very variable from hour to hour. And so, a 24-hour average, the next day doesn't really tell you much about what's going on today, what you can expect later on down the road either. So, too bad Claudia left. That was a picture of her putting up a smoke monitor. But yeah, that's good. Yeah, perfect. So, so there's a couple different steps with going from a visual range to a PM 2.5 concentration. And so first, there's a human-sighted visual range, just trying to estimate how far you can see in the atmosphere, and then taking that visual range and converting it to a PM 2.5 concentration. Actually, can you go back one slide? Yeah. Claudia. Oh, I just went through this about, how we... But in the case when you don't have monitors... But yes, this is when Claudia was deployed as an air resource advisor, actually the summer before last, putting up a monitor. Yes, I was out there with Claudia. We went over Hillendale. So anyway, okay, next slide. So yeah, human-sighted visual range, and then going from that visual range to a PM 2.5 concentration, and then going from that PM 2.5 concentration to a health impact. So there's uncertainty associated with each step of the way. So I'm just going to try and highlight some of those uncertainties. So next slide. So what is a visual range? And so a visual range is defined as in the context of how far away a black object has to be such that it's just barely noticeable. So that's there's a couple key parts here where it's a black object. So it's not a green object or a white object. It's a black object, and it's that point where you can just barely see it. And that point where you can just barely see it is also dependent upon the observer, and the observer's vision too. So, so here's just a picture of the Grand Canyon and different points in a vista and how far away they are. And so next slide. So where did this all start? Well, about the turn of the century, way back in 2000, in Montana, there was with the person at their Montana Department of Environmental Quality, City of Helena was getting impacted by wildfire smoke, and the person at DEQ realized that he had 1 hour PM 2.5 concentrations and also had ASOS visibility information from the airport. So using ASOS visibility and these 1 hour PM 2.5 concentrations, just correlated them together. And so with this correlation, they came up with this chart, and so correlating a short-term 1 hour PM 2.5 concentration with a visual range, and so that's what the second and the last column are, and then applying different factors to that 1 hour concentration to get 8 hour and 24-hour concentration. Thanks. So. So that was the initial cut. That's where this all started, essentially. And so And a couple caveats to it is that this is only good when you have low relative humidity and when you have high smoky conditions. So it's not necessarily applicable to when you have other pollutants mixing in or when you get relative humidity playing a role in things. And the relationship that John Cofield at DEQ came up with, it was PM 2.5 times visual range equals a constant of 450. And visual range in this case was in miles and PM 2.5 in micrograms per meter cubed. And that's just the relationship that fell out of the data that he was looking at. So next slide. So then what came next is the Wildfire Smoke Guide, Wildfire Smoke Guide for Public Health Officials. And so a lot of agencies were involved in this publication, a lot of California agencies, but Montana was involved, and EPA at the federal level was also involved. And so here's a table from that publication right here. And again, taking a short-term 1 hour or 3 hour PM 2.5 concentration and linking it to a visual range. And again, this visual range is only linked to this short-term 1 to 3 hour PM 2.5 concentration. It's actually not linked to the 8 hour or the 24-hour average as you see here. And so that table, perfect. That table is just a little, in the Wildfire Smoke Guide, is just a little bit different from what Montana came up with. And so here's a chart of what different agencies are using for health breakpoints for short-term PM 2.5 concentrations. And as you can see, there's differences here. So here's the Montana setup right here, what they defined for as far as what good is in PM 2.5 concentration terms and what moderate, unhealthy for sensitive receptors and so on is. And then here's what's in the Wildfire Smoke Guide. Alaska and Colorado did something a little bit different. Manitoba up in Canada followed closely what Alaska and Colorado did, but they decided to get rid of the moderate. Well, they combined the moderate and unhealthy for sensitive groups. And then Canada, this is an interesting one I just kind of tossed up here too, is Canada has an air quality health index as well. And that actually is combining PM 2.5, ozone, and NOx together into a single index. So that's the first time we've seen, or that I'm aware of a multi-pollutant health index. And that was defined based upon urban areas too. So the calculations that went into this were for smoky conditions, but still that's a new application to that index, so use it loosely, I guess you could say. So next slide. So then discussion was generated in the National Wildfire Coordinating Group Smoke Committee, which, good timing, Pete heads up here. And so I participate in the NWCG Smoke Committee. Pete leads up the NWCG Smoke Committee. Greg participates somewhat, and Josh as well. And so a member of the committee brought this issue for discussion to the committee because he had been contacted by states in the Southeast who were interested in applying the guidance that was in the Wildfire Smoke Guide, which, and if you remember, the guidance is specific for low humidity environments, and so, but the Southeast needed something as well, and so they were interested in it. So it generated discussion. And so we talked about what are the consequences of using a human-sided visual range. There's multiple approaches currently in use, and then there's the influence of relative humidity. Also, different aerosols can be hygroscopic. In fact, they can have a high affinity for water, and that, when you have higher relative humidity, that combines with things. And then you can also have other anthropogenic sources coming into the mix when you have smoky conditions. So next slide. So here's just an example of how humidity can have an impact on a visual range. And so I realize this is New Mexico. It's not a big worry, but just wanted to just show this as an example. So this is Great Smoky Mountains National Park. And in both of these pictures, the PM 2.5 concentration is the same. It's 21 micrograms per meter cubed. But as you can see, the visual range is quite different between the two. One's at a relative humidity of 30%. The bottom one is at a relative humidity of 90%. And so the visual range goes from 47 kilometers down to 19 kilometers. And so this was generated using the wind haze program, using data from the Interagency Monitoring of Protected Visual Environments improve data. And so, and so here's the improved light extinction equation. And so we started talking, we started thinking about all of these things and knew that the improved data was out there, so started analyzing some of the improved data. And really what this just shows is the different constituents of PM2.5 and how they can contribute to light extinction. And then that light extinction can be related to a visual range given with a constant involved known as the Koschmider coefficient. And there's a lot of assumptions that go into this this equation right here and the Koschmider coefficient that I'll get into a little bit now. So next slide. So with the analysis that we did, using improved data and looking at those, equating those equations, flipping things around to solve for things in terms of fire. So fire puts out a lot of organic carbon. We came up with a relationship. There's a relationship now between visual range and PM2.5 focused on fire. And it also came out with, actually, I was surprised at the curve fit that came out here. And so where you have PM2.5 times visual range equals a constant of 622. And this is a case where visual range is in kilometers. And so that's what this black curve is that equation, that relationship. And then laid on top of it are the breakpoints from the Wildfire smoke guide. So actually the breakpoints from the Wildfire smoke guide laid quite well on top of this curve. But looking at this too, then realized that, once you get below about 5 kilometers here, whether you're in unhealthy for sensitive groups to unhealthy to very unhealthy, that's, small like error in a visual range estimation can, flip you from unhealthy to sensitive groups up to very unhealthy quickly. And so there's so we noticed that. So next slide. And then this is just another look at things. The table's color-coded by the air quality index colors, and on the y-axis here, we have visual range in miles and in kilometers, and then across the top there's different values of relative humidity, and these values are essentially plugged into the improve equation to calculate PM2.5 concentration. So that's actually the numbers that you see here in the table, and then they're color-coded to the air quality index colors. And so what we see, though, is that at the higher relative humidities, you can, let's see, for example, like at a distance of about 7 kilometers here at a relative humidity of 90%, your air quality is still good. Yet if you were at a relative humidity of lower than that, your air quality would be in the moderate range, and you could jump up to about 60 micrograms per meter cubed. So just another illustration of how relative humidity is important in the whole thing. Next slide. So then this brought on a JFSP, Joint Fire Science Program, ended up being interested in it, and they ended up being, Pete went and talked to the JFSP, and they sponsored a project to investigate this further. And so then Bill Malm, who's a researcher, actually retired now, but he was a researcher for many years with Circa and the National Park Service. Circa is at Colorado State University, and the National Park Service Air Resource Division. Bill Malm and Bext did quite an in-depth study of all of this. And let's see, make sure I'm doing okay on time. Okay. And they had several goals of the study, but some of which are they wanted to quantify the uncertainty in estimating a visual range, and also the uncertainty of going from that visual range to a PM2.5 concentration. And then they wanted to make recommendations, look more closely at the relationship when you multiply visual range times PM2.5 to get a constant value. They looked more closely at that relationship, and also how that relationship can change across the country. So next slide. So, these next couple of slides are going to be about the quantification of that uncertainty and different elements of of uncertainty that comes into play when you have a human-sided visual range and when going from that visual range to a PM2.5 concentration. So one of the things that we're uncertain about is when the target is not black. So part of the Koschmider equation and assumption is that the target that you're looking at is black. You have a black body against a bright, background. It's sun is shining on it. And so when the target is not black, which is typically, what we're looking at is not black. We might be looking at a dark mountain that's forested, so it might be a dark green, or you could even be looking at a snowcapped mountain. So that adds more uncertainty to what you're seeing and what you're estimating. And so in the case for this study, Bill actually was rather conservative. Assumed that it was probably most of the time going to be a green covered surface, a mountainous surface. And so assuming that, the uncertainty is about 0.15 in this case. And then that uncertainty gets higher for the lighter colored surfaces. So go ahead. And then there's also uncertainty when an observer is looking at a target and judging when it reaches that threshold constant. So judging when it reaches that point where you can just barely see it. And so that uncertainty was quantified at between 0.2 and 0.3. And so then these are just some pictures of another Class 1 wilderness area where in the top you can get an idea of how far away, some of the landmarks you're looking at. And then on the bottom, let's see, at least Black Mountain, at 46 miles is totally obscured now. So trying to judge when that that distance of when that obscureness actually happens is hard. And then this is a big one. When there's a non-uniform aerosol distribution between the observer and the target. So if you're looking at some target, 5 miles away, 10 miles away, 2 miles away, you need that the distribution of particulates across that line of sight needs to be constant. And even though it might look like a rather uniform haze, I bet that it's not all that uniform always. So smoke is highly variable, and so there's a lot of uncertainty introduced into that, and Bill quantified that at 0.5. Okay. And then here's a final one, again mentioning relative humidity. Taking into that effect, Bill looked at this effect at various points across the U.S. and so kind of had a Western, looked at things in the West and looked at things in the East, and quantified uncertainty between 0.7 and 1, taking into account relative humidity. So next slide. Bless you. So putting this all together, one of the conclusions out of Bill's report is that there's about a factor of 2 of uncertainty when smoke dominates. And this factor of 2 applies both to the western U.S. and to the eastern U.S. And if you apply that factor of 2 to the PM2.5 concentrations that are given at the different breakpoints, for example, in the Wildfire smoke guide, you get these uncertainty bars here. So the black uncertainty bars. So the black points are the data from the Wildfire smoke guide. So 10 kilometers, you have a PM2.5 concentration of, I think it's around 100. And then you apply a factor of 2 uncertainty to that, and you get these uncertainty bars on that number. And so kind of what jumps out here then is that when you get to the lower visual ranges and the higher PM2.5 concentrations, your uncertainty bars overlap a lot. So whether you can say you're in unhealthy or even hazardous conditions, it's a very fuzzy line at this point, given all the uncertainty that goes into these estimations. And so just to kind of put this maybe in perspective, this x-axis is in kilometers, and so 10 kilometers is about 6.2 miles, so 5 kilometers is about 3.1 miles. So probably when you're getting down below 3 miles, it all becomes, one big blob. So, okay, next slide. And then this is just a visual perspective of the previous graph. And so this is actually a background of Dallas. And, but I chose this out of Bill's report because you could see it just had a good visual line with the buildings here. And so at the so the 38 micrograms per meter cubed is the break point for the good category in the wildfire smoke guide, and that corresponds to a visual range of 17.1, about 18 kilometers. And then if you apply the uncertainty to that, that actually means that, you know, at a concentration of 38 micrograms per meter cubed, your visual range could maybe be between like 8 and 37 kilometers. So there's uncertainty here. And then going to the next level, this is going into 88 is the break point for between, so from 38 to 88, you're in the moderate, you're in the moderate category. And so 88 corresponds to a visual range of about 10 kilometers. And again, you can see what the uncertainty does to that visual range estimation then too. And this is using the wind haze program to fog up these different images so you can visually see what those visual ranges would look like. Okay, next slide. And then okay, so that was Bill Malm's report. I just also wanted to mention an effort that Joint Fire Science Program also sponsored was a smoke photo guide, and Josh Hyde worked on a lot of that as well. And so this is just an example of see this picture and the next picture from the smoke photo guide, and this is the Grand Canyon, and this is on a very clear day where PM 2.5 is less than 5 micrograms per meter cubed, and you've got a visual range of almost 50 miles, and so different landmarks are cited here in this figure. And then if you go to the next one, you can see what happens when PM 2.5 goes up to a much higher level, 245 micrograms per meter cubed, and your visual range goes down to about, well, 2.3 miles in this case. And the smoke guide is designed, it has pictures like this for various sites across the whole U.S. So this is Arizona, so representative of the Southwest. There's another site for Colorado, for the Central Rocky Mountain site. So there's selected sites across the U.S. that you can use this as a guide to maybe visually give you an idea of what visually PM 2.5 might look like in the atmosphere that you're in for your region. I hope I explained that correctly. Okay. Okay. Thanks. Okay. So next slide. Here we go. This is really the end. So I just wanted to list some of the resources and references if you want more information or the citations for some of the stuff I talked about. So the top one here is the report by Bill Malm and Brett Schichtel, and it's quite the report. And then just some other publications: the Wildfire Smoke Guide, the Canada Air Quality AQHI, the Wind Haze Program, the publication that came out of the discussions we had in the Smoke Committee. And I think that's it. Yeah, so, okay.